Opportunity to my longtime friend and collaborator, Risa Wechsler. So Risa, if you'll pardon the sports terminology, came up as part of a golden generation of graduate students at, this is not a joke.
Not a joke.
Golden generation of graduate students from Joel Premack's group from Santa Cruz in the late 90s and early 2000s. I was tempted to say turn of the century, but that, okay, joke. All right. And then she went to first postdoc at University of Michigan as a prize fellow, and then to University of Chicago after that as a Hubble fellow, which is where we first met, as I was on my first postdoc there working for Andrei Kravtsov, where we kicked off a number of long-standing collaborations.
I thought that's the golden generation you were going to refer to, so I was. So
oh, no. That's the golden generation of postdocs.
Yes. Okay. Good.
But now she's been busy creating her own golden generation out of her group at Stanford, which is immensely productive, a group of students and postdocs, a number of which we have actually had here in the many years since we have previously invited Risa, which was back in Meyer, to her own students and postdocs to be giving Astro Seminars in the interim. She's also the director of their Cobley Center at Stanford, CIPAC, as well as the director of a new center on decoding the universe, joint with Stanford Data Science. Also former scientific spokesperson for the DESI collaboration. And if that's not enough, she's also the world expert on the galaxy halo connection, which is permeated pretty much all of cosmology, both in galaxy formation, constraining cosmological parameters, testing cosmic acceleration, and also probing the nature of dark matter, which is what she's going to tell us about today.
Oh, but you left out one. She's a member of the National.
Oh, that's
5 minutes ago.
Are you serious?
I'm serious.
I have a story for you, which is that I think it was right around my birthday in March, the first week of March in 2006. In 2006, some of you were in the room. It was in the other building. I was about to give a seminar at NYU. And about an hour before I gave the seminar, Roger Blanford called me and told me I had a job at Stanford. So that seminar went great. It was amazing. Okay.
It was a good seminar, I think. Did you give it from your phone?
That may have been another one.
There was one where you were on.
Oh,
you were just on your phone.
Your phone, that was the whole thing. Yeah.
Yeah, we were just.
Well, that's when Andreas was texting her during that.
Anyway, well, this goes back away.
Thing that was 19 years ago. Oh my God. One more thing is that even though I've known some of you a long time, and I know that I should have prepared a talk with half the number of slides, I did not do that. So we're going to be here for hours. Okay, so first, just as Jeremy mentioned, I have an absolutely incredible team of current and former students and postdocs. So they did all the work here. I'm just trying to put it together. And I'm going to also tell you about work that I've done with many collaborators in current and nascent collaborations. I actually just came from a collaboration meeting from this brand new collaboration VIA, which is kind of the punchline of my talk. So really excited to tell you about that. Okay, that's what I thought. It's not working. For some reason the advancing is not working. So let's try one more time. Okay, I'm getting this this bizarre screen sharing is paused version. Does anyone know? This is like a mysterious thing that happens sometimes in Zoom. I should do it with my phone. It's not advancing and I just don't know why. Maybe I'll go share the whole screen. That might be.
Yeah, that might be easier. Yeah, because it's changing the focus in some way, and that's why that happens.
Let me try to share again. Okay. I'll share the whole thing. And let's see if that works. No, it doesn't work. What's going on here? Oh, too many key. Oh, yeah, yeah. Okay. Now it's working. Okay, great. Okay, yeah, so I'm gonna tell you about what we know recently, but mostly about what we will know in the future from new measurements and how we might in potential learn more about dark matter from the smallest scales that we can really measure robustly. So first, I'm just gonna start by saying this is gonna be a really, really exciting decade for all of us. Whatever thing we work on in astrophysics, if your favorite mission is not on here, I'm sorry. There's so much happening.
It's not.
Okay, I know, I'm sorry. It's just, these are the things that, you know, mostly I'm thinking about the first two rows and, you know, I think it's very, very exciting times and lots of precision that is coming at us, lots of multi-wavelength surveys. Again, this is incomplete, somewhat self-centered version of this plot. I'm sure I've made some mistakes that will offend Blanton, but in any case, you know, we've just, you know, we're kind of just in the last few years jumped into this really new regime where we've kind of grown our numbers by an order of magnitude. We now have, you know, 20 million galaxy spectra. It might even be more than that. 15 million stellar spectra. We're doing lensing with 300 million objects. We've got about 60 low mass galaxies in the Milky Way, and we've got this incredibly precise measurements from Gaia. And the future is looking even more exciting, not just from the numbers, but also increasing resolution and going to higher redshift and, you know, et cetera, et cetera. So it's exciting times. A lot of these missions are primarily cosmology driven, not all of them, but many of them, and they are going to test the standard cosmological model at really incredible precision. You know, just this is kind of like off the top of my head, something like 1% precision on the Hubble parameter from many methods, better than 1% precision on the expansion history, about 1% precision on the growth of structure, new constraints on tensor to scalar ratio, new constraints on neutrino physics. So lots of exciting things happening. I'm not going to talk about any of that. I'm going to focus on dark matter for this talk. In particular, I want to ask, you know, what can we learn about dark matter from the cosmos? And in particular, I'm just going to be focusing on some of the cosmic probes we have of dark matter, particularly those that are focused on the smallest observable scales of structure formation. And, you know, one way to ask that question is just to say, can we detect any deviations from CDM? Any deviation we can find is definitely interesting. Another way to ask that question is, can we actually rule out CDM by, you know, in that way? Or can we rule out lots of other models by consistency with CDM at much smaller scales than we know now? The thing that I'm particularly excited about, because I think it is an achievable goal in the next decade, is to actually figure out what is the minimum mass that can host a galaxy today, and then to find dark halos at lower masses than that. So we have not yet done that. I am optimistic that we could do that within about a decade. And I think that's very, very exciting. So to set the stage, this is just the power spectrum as a function of wave number, large scales over here, small scales on the right. And, you know, these are lots of measurements from CMB, from large scale structure surveys. And the gray line here is sort of what we call CDM. And, you know, from the perspective of structure formation, what we mean when we say CDM is that the free streaming length of whatever particle is the dark matter is small enough that it doesn't impact structure formation on any measurable scale. And that there are interactions, if there are interactions, that they also don't impact structure formation. So in the context of this talk, that's what I mean by CDM. Okay, so CDM makes a whole bunch of predictions. You know, interestingly enough, most of these predictions have been around for a while, including from those golden days that, that Jeremy mentioned. You know, essentially, as soon as we were able to calculate structure in CDM, people started trying to make these kinds of predictions. And they're quite rich, right? CDM, you know, given CDM model predicts the number of dark matter halos, how they cluster, their internal structure, how they accrete over time. And so it's actually a very rich set of predictions that has been kind of around for a while, but is only really starting to be observationally accessible. So CDM is very well tested on large scales, and it's actually most of the things on this screen, well, actually this clustering is now very extraordinarily well measured, but many of the other things are not as well measured. And, you know, could be that we don't have CDM, or that there are other dark matter models that are very interesting. These, many of them make different predictions for small scales, even if they look identical to CDM on large scales. And so some examples of that are warm dark matter that's very light, self-interacting dark matter that where there's a dark matter proton interaction, a dark matter that decays late. And these are just examples. There are a lot more. I learned about another one yesterday and another one today. So there, you know, there's a lot of different models that actually can potentially impact small scale structure. And so we should try to make these measurements as well as we can. And so just coming back to this plot, you know, this is some examples. And most of these models here, these lines, this is for, you know, a particular fuzzy and interacting and warm dark matter model. All three of those are examples where there's a tunable parameter. So it's not so clear that it's exactly here. This purple line could move to the right or the left. And so, you know, we'd like to be able to actually push those measurements down. So the context of this talk, I'm going to basically ask the question, can we make good measurements in this regime so that we can either see evidence or rule out some of those models that could impact that regime? Okay, so lots of interesting potential probes of small scale structure. I'm going to talk about the ones on the top and not the ones on the bottom. The ones on the bottom are interesting. I think Lyman alpha forest is developing really nicely. High redshift galaxies are interesting, but probably not quite as competitive. Oh, someone's calling me to congratulate me.
She didn't believe it.
Yeah, that was my turn. And 21 centimeter, I think, is actually really exciting for this, but not yet there. So, okay, so I'm going to talk about these top three. Dwarf galaxies, stellar streams, and the gaps that might be created in those streams, and strong lensing. So I would claim that dwarf galaxies currently have sort of the strongest constraint on small scale structure, although there are similarly competitive measurements from lensing and Lyman alpha forest. The dwarf galaxy measurement that constrains small scale power is extraordinarily simple. It is just that there are small galaxies and they live in dark matter halos, and therefore those halos must exist. So it's a very simple measurement. And these measurements are about to get a lot better. There's lots and lots of ways we can improve these. And both in terms of the power as well as the power to constrain self-interacting dark matter. These other two probes, I think, are very, very interesting, and they have potential to go further than dwarf galaxies. So I think they have near-term potential to probe smaller scales and actually confirm or rule out this key prediction that in CDM there are dark halos that are too small to form galaxies and have no stars. So I'm going to briefly touch on these 4 different surveys and just say that, you know, I have a column here on the left, spectroscopy, imaging on the right. DESI and Rubin Observatory are surveying most of the sky, or at least a third to a half of the sky. And these things here, this is a new spectroscopic survey I'll tell you about that's much higher resolution. And the Roman Space Telescope, which also has high resolution and just put out its survey strategy, hopefully will launch in late 26. Okay, so I'm going to start kind of nearby in the Milky Way. You guys have, many of you have heard of these results. These are not new. But, you know, there's been in the last, 15 years, huge discovery. Actually, some of this discovery started here at NYU of new population of very small dwarf galaxies, and any of you who are in the audience who haven't seen these are very hard to find because they're sort of just a very small number of stars on a confusing background, and so you really need regular sky surveys to be able to make these kind of measurements. But we now know of about 60 galaxies that are in the Milky Way that were accreted over the Milky Way's history and are still observable as distinct things. Many of them have very painstakingly taken velocity dispersions that tell us they live in halos that are much more massive than the number of stars. So the smallest of these have just 300 stars, or 300, it's not 300 stars, 300 solar masses. Most of the stars are actually smaller than 0.8 solar masses, and they live in halos that are, you know, probably around 10 to the 9 solar masses. Okay, so coming back to the dark matter side, right, an example of a model that suppresses power is warm dark matter, and this plot shows the mass of the subhalo as a function of the subhalo mass function suppression. So in this plot, 1 is CDM, and anything that's less than that is something that has suppressed small scale structure. Now, if you don't have galaxies, you can also suppress structure, and you know, because here we're talking about the counts of galaxies. And so, but if you actually count those galaxies, you can say, okay, well, we must have had the halos that host those galaxies, and so we can rule out the things that are really suppressed. Now, that suppression is partially degenerate with, you know, which halos are massive enough to form galaxies, but that's something we can marginalize over conservatively. So, and they're not entirely degenerate. They do make slightly different predictions. So, as I said, different models make different predictions for substructure. This is just an example of 3 models: thermal warm dark matter on the top, a fuzzy dark matter with, you know, which has a mass, a very, very light mass around, you know, around 10 to the minus 22 eV, and then a model of interacting dark matter where there are proton dark matter interactions. And you may have seen some of these kinds of plots in the past where they're really dramatically different things, but those things that look very different from CDM have actually already been ruled out. So this is from a recent paper. Oh, another call. Okay, sorry, very distracted. So the middle row is kind of where we are right now in terms of things that are just on the edge of being consistent with what we're measuring now. The ones on the left are basically already ruled out, and the ones on the right, we might be able to probe in the future. And one interesting thing is that, you know, different dark matter models, depending on what they are, can make more complex predictions. So in many models, the simplest thing you can do is just talk about the number of clumps. But in principle, some things can also make different predictions for the radial profile, within halos for the inner density, especially self-interactions can impact the inner density for the anisotropy. All of those things can potentially have an impact. So a few years ago, we did this analysis. It was the first time that we did sort of a comprehensive analysis where we really tried to do about 3/4 of the sky and really understand the selection function. And so what you're doing is you're taking a given model, understanding how much it suppresses structure, turning it into a luminosity function, and then doing a whole constraint where you marginalize over, you know, the galaxy halo connection, the properties of the Milky Way, etc. And the bottom line of this analysis, which is
Sorry, can you?
Yeah.
That last. So.
the last step, yeah.
Yeah, this first arrow seems
You're okay with that,
fine.
yeah.
Yeah, the last arrow.
Yeah, I know.
Why? Like.
Yeah.
Like you do have some sense of the velocity dispersion of this distribute. Like
So-
you could put that on the x-axis, right?
We could, but we didn't in this analysis.
Okay.
So we and part of the reason for that is that it's just it's harder and it requires a lot more assumptions, and we wanted to be very conservative. So that definitely does. So
why does it require more assumptions than the luminosity? Like the luminosity, you're getting something about the star formation history and
Yeah.
all that, right? Like
This
that
is
seems
like-
harder.
Yeah, so so if I wanted to really predict it and use that prediction as a additional part of my constraint, I absolutely agree it would be harder and the velocity would be easier.
Uh-huh.
But you can think of this as like abundance matching or like a very simple pasting exercise with a scatter.
Okay.
So I make an assumption that massive luminous galaxies live in more massive halos with a scatter. And I marginalize over that scatter and the relation.
But you're abundance matching to what, if not the luminosity distribution itself?
The luminosity distribution itself, yeah.
So by design, you
The
get
whole-
this last step.
No,
No,
no.
but you're matching to this distribution.
Sorry, I didn't even include the plots on this
Okay.
because let's get into it afterwards. But let me try to explain it this way. Let me ignore the scatter for a minute.
Yes.
Okay.
please. Yeah.
I'm going to put the LMC in the most massive satellite. I'm going to put the SMC in the next most massive satellite.
Mhm.
Right. And I'm going to just say, and then I'm going to say, okay, I know there are 60 UFDs or maybe
Okay.
50 UFDs in the Milky Way. Therefore, I better have 60 halos.
I see.
That's all.
So you're
really-
not guaranteed that this will work all the way down.
That's right.
Okay.
That's right.
Got
Exactly.
it. Okay.
Exactly.
Thank you.
Yes. So I think the real thing I want to leave you with, because I'm not going to have time in this talk to go through the details of these models, because I want to talk about other things. The thing I want to leave you with is that even this current analysis basically says that whatever model you have for what the dark matter does cannot suppress the subhalo mass function by more than about 25% at a few times 10 to the 8. So some of the galaxies that we already know live in halos that are 10 to the 8, because otherwise there's not enough halos. And if you suppress it too much, then you can't get those galaxies.
Can it enhance it by 25%?
Yeah, so we did not, in this analysis, we didn't put any constraint on the enhancement. And this analysis doesn't constrain the enhancement because of this thing that I was trying to explain maybe poorly to Mike, which is that if you have extra halos, that's fine in this analysis. In principle, that is totally doable with the velocity measurements, which we should incorporate and needs to be done. Not all of these have good velocity measurements and they're tricky, and I'm going to come back to that later in the talk. Yeah. Okay. So lots of ways we could potentially improve these constraints. So one of them is to use measurements of the masses or the velocities of the satellites. Another one is to find more. There's actually is an uncertainty that just has to do with the mass of the Milky Way and its accretion history, because there can be a big scatter in what you predict. There are many ways to improve the modeling. So here we were quite conservative about, say, what tidal stripping does to the satellites, and that's something that we should be able to do better. It actually helps to find satellites in additional external systems because you break key degeneracies that way as well. And I'm going to talk briefly about a few of these, but mostly I'm going to focus on the last one, looking at other methods. Okay, so I want to just briefly mention your Rubin Observatory. If anyone has not heard of this, it is an incredible 3.2 gigapixel camera that we built at SLAC. And it is going to start taking data very, very soon. For about 10 years, it will image the whole southern sky on average every 3 nights, about 15 terabytes of data a night. And just 2 weeks ago, the first photons came through the camera, and I have not seen the images, but these people have, and they look very, very happy. I expect that you all will be able to see these images in about 2 months. So stay tuned. Super, super exciting. It's going to be great. So of course, one of the exciting things that Ruben will do is find everything that changed. Asteroids, supernova, variable stars, eclipsing binaries, gravitational wave counterparts, lots of things we never thought of before. Really fun. For the purposes of this talk, there's a few things that I'm going to mention. The first is it will make fantastic lensing maps with about 10 billion galaxies. We expected to find about 100 new ultrafaint galaxies in the Milky Way. We expected to find more detritus of things that were accreted onto the Milky Way and got destroyed. And we expect to find lots and lots more new strong gravitational lenses. So just to give a sense, it'll have about 1,000 times the volume as we have now for resolved stars. And there's a nice analysis that came out just last week that uses very realistic predictions for what LSST should find and finds that it will find about 100 new satellites in the Milky Way. So that is very exciting. I was briefly going to mention a couple of things from DESI. Primary thing that DESI is doing is measuring the equation of state and the growth of structure. And that is beautiful, beautiful work. And I'm not going to talk about it, but I'm happy to discuss it over coffee or dinner or whatever. It also is really good at finding small galaxies and mapping the Milky Way. So there's a really nice survey that Jeremy, a few others here have been also working on called the DESI Bright Galaxy Survey, which you can think of as like the Sloan Main Survey, but 2 magnitudes deeper. And then there's another survey that we've been pursuing as a secondary target program, which takes that another 2 magnitudes deeper to get more dwarf galaxies. And we actually have already spectra for about 16 million stars in the Milky Way. So this is just a little side thing that I'm just going to tell you about 2 tiny things that we're doing with these data. Postdoc at Stanford, Christian Aganze, has been looking for structure in the stellar halo. So this is just fun. There was this stream that was found in Sloan and then never mentioned in the literature again. So we actually refound this in the spectra. And so this is using clustering with the DESI radial velocities plus Gaia astrometry. And so you can make a really, really nice map actually of this stream. We got some follow-up data with Magellan. And it's just an example of actually finding structure in the spectroscopy when you have a really, really large survey. I just want to briefly mention this dwarf galaxy catalog. The background image here are images of the many hundreds of thousands of galaxies that we now have from DESI that we have spectra for. So this LOSI survey that I have been pushing on as the secondary target proposal, we spent about 10 years doing a survey called SAGA, trying to get satellites around Milky Way analogs, basically from 20 to 40 megaparsecs away. And we learned really well how to find dwarf galaxies, and we're now using those techniques to find dwarf galaxies over the whole sky. One of the things we'll be able to do with that, combined with LSST, is actually measure lensing profiles for those dwarf galaxies. So actually the error bars there are a real measurement we made, trained on a very small amount of data. Those measurements will get much better in the future. This is just fun. This is from literally yesterday. My graduate student, Viraj, found a supernova as an outlier in these surveys. I don't know a lot about supernova spectra, but it's just a fun little tidbit. Okay, I'm going to get back to the main plot line here. So CDM tells us something very simple, which is that the halo mass function continues down well below where we have measured it so far. Okay. In any theory of galaxy formation, you need a certain amount of gas in a halo to be able to form stars. So if you remember what I told you earlier, I said that some of the galaxies that we have already detected in the Milky Way live in halos that are a few times 10 to the 8. And so if you look at various predictions for where galaxies should, where halos should stop forming galaxies, it's not much more than an order of magnitude below that. Actually, a bunch of predictions were higher than that. If you look at only H2 cooling, if you look at only H1 cooling, then you would already have seen the limit of galaxy formation. So this plot here is just the fraction of halos that have a galaxy as a function of mass. At some mass, it's definitely 1. At some very low mass, it's definitely 0. And we want to find like where this turns over. And then ideally, we want to find not just where it turns over, but we actually want to see evidence that dark matter halos exist below that. So if we confirm those, that's a really clean prediction of CDM. And it says that, very basically, dark matter has to exist, not in galaxies. So that's nice. If you are really convinced that you have an experiment that's sensitive enough to do this and you don't find them, then you rule out CDM and you say, well, okay, dark matter looks like CDM on large scales, but it does not look like CDM on small scales. Okay, so how do we do this? I think there's 2 potential ways to do this: gravitational lensing and stellar streams.
Can you go back?
Yeah.
The meaning of no.
Yeah. Good.
Is you find very low mass halos with galaxies in them. That's the meaning of no.
No, the meaning of no is that you are convinced you should be able to find 10 to the 7 solar mass halos, and they are not there.
Okay. All right.
So
The halos aren't
the
there.
halos are not there. The halos are not there. At some point, the galaxies have to disappear.
You need a gravitational antenna
Okay,
that
so-
doesn't go off.
Yeah, a gravitational antenna that doesn't go off. That's good. Yeah.
Okay.
Like no mono.
Then how does finding this mass threshold help you determine whether or not the halos are there?
It doesn't tell you whether the halos are there, but it tells you that whether or not there are halos without galaxies. You don't buy it?
Now I got confused.
Well, no, I'm just a little confused. You're
Okay,
saying
good.
you're saying, okay, the small halos have to be dark. So you want to find out at what mass halos go dark.
Yeah.
But their halo's still there. Like, so what does that have to do with whether or not the halos are there?
No, then you either find the halos or you don't find the halos.
But she's talking about detecting dark halos below the threshold, and you haven't told us yet how you'll.
Oh,
do
I
that.
see.
I haven't told you how I'm going to do
But
it
you're
yet,
going to, I
Okay.
think.
but that's what's next.
Good.
That's
Oh,
what's
I
next.
see. And can we detect the dark halos? Fine.
Yeah.
Fine. Sorry.
Okay.
I'm reading comprehension.
Okay, no, it's all good. Okay, so I haven't told you how we're gonna find them yet. Now I'm gonna tell you that. Okay, two ways to do it. Sebastian here has been leading this work. This is a nice figure from his paper. So basic idea, right, is that you have a source galaxy back here. You have a lens here. In that lens, you have a massive dark matter halo. That massive dark matter halo is full of little clumps. And you want to see what the clumps do to the image of the source. Okay, so this is an example of if you change the normalization of how many halos you have, you change what the image looks like, and you can actually kind of read this subhalo map out of the image. Okay, so that's the basic idea. Turns out this is not very easy to do. So first thing you need, this is gonna be a simplified version, and you have Sebastian right here who can tell you all of the details. So simplified version, the first thing you need is you need a lot of lenses with great images. So right now we have about 30 strong lenses from HST that are really nice for this analysis. There's maybe 100, but 30 is a good number that is easy to work with. That number is going to get bigger quickly. Both Euclid and Roman should be able to do this kind of analysis. And just last week, so I co-chaired the committee that worked on the survey strategy for the Roman High Latitude Wide Area Survey. And it's going to be a 2-part survey. Basically 5,100 square degrees, about half of it is 1 band and the other half is 3 bands plus spectroscopy. Super cool though, because there'll be a strong lens in essentially every Roman pointing. So very, very exciting to think about getting these data. Roman, is essentially 100 times Hubble, so it can do things much faster. Okay, next thing you need is a robust inference pipeline. So, these substructures are very hard to detect in this image. So really the only way we know how to do it is to forward model everything, to basically take the source, run it through the lens with the substructure, try to then actually infer what you get out of a large number of images. So we've been developing this simulation-based inference pipeline that simulates lenses with different amounts of substructure. And in this analysis, we show that we can get unbiased measurement of the substructure mass function with more than 100 lenses. Okay, robust is not enough. It also has to be fast. Sebastian has been working hard on this and made a lot of really interesting methodological developments, including using this nice technique called sequential neural posterior estimation. And that has made our analysis very, very fast. So this is a really nice problem where the simulation step is actually as fast as the inference step. So that's great. And then you also need a large sample of representative source galaxies. So it wasn't obvious that this was going to be a very important limiting factor, but it is now the limiting factor. And an interesting thing about this is that I still don't know how good this analysis is going to do. All I know is that it's going to be better than what we can do so far.
And galaxy, like when people have thought about this in the past, they've normally thought about quasar lenses and like anomalous
Right.
fluxes. And you want to use galaxies because they're more galaxies or because they're better at this, or why?
I think they're better at the substructure problem. You actually, the structure in the source galaxy actually helps you. It's confusing, but it actually helps you. Is that a reasonable answer, Sebastian?
Yeah, and the quasar version of it, you're competing with stars that also produce microlensing for the magnification areas you're talking about.
Yeah.
And so that's your leading uncertainty that's very hard to destroy. Whereas here, since you're like looking for larger scale deviations, it can't be produced by the microlensing effects of stars. And so you don't have that degeneracy stopping you from constraining your signal.
Because the source galaxy is smooth on the scale of like this.
Yeah, it's smooth
Speckling.
and extended over the sky versus the quasar is essentially a point source.
Yeah. Okay, thanks.
So Sebastian and a graduate student at Stanford, Sydney Erickson, are currently working on increasing the training set sample because that's an important factor. And then the last thing that you need is you really need to have good predictions from dark matter models, including even CDM, where those predictions I would say are not yet good enough. And that's what I'm going to talk about at the end of the talk. So we're working towards doing this full analysis on 30 HST lenses, and you can hear about it soon from Sebastian. Okay, so I'm going to move on to the next potential probe of small scale structure, which is that the Milky Way is really wrapped in stellar streams, things that have been accreted over its history and have been tidally disrupted. And it is also full of subhalos. So the thing that we want to look at is the interaction between these two things. The interaction between the things that have come in and left these streams and these little things that are spinning around the Milky Way at 300 kilometers per second. It's about 100 streams from dwarf galaxies and globular clusters that are now detected in the Milky Way, and we're certainly expecting more. So this is a really exciting field. So the basic idea, right? These stellar streams are created either by dwarf galaxies or globular clusters that are accreted onto the Milky Way, and they're relatively thin, right? Low velocity dispersion, and so if something bumps into them, you should be able to see a feature, and this is a nice little movie by Anna Banaka showing a stream evolving in a potential, and there's a little halo that pops through it and makes a little feature. Okay, so this is really interesting. It is also really hard, and I will say that I was very skeptical about the prospects of this for a long time. And the reason it's really hard, so I told you that ideally I want to get down to like 10 to the 6 because I really want to find these dark things. And this is roughly in velocity space what it looks like for a 10 to the 7 and a 10 to the 6 solar mass perturber. So, you know, of course, it depends on many things. It depends on the impact and et cetera. But, you know, you can see this, but it's hard. And then when you add velocity errors, it becomes really hard. So most current stellar spectroscopy has few kilometer per second velocity errors, radial velocity errors. And so if you really want to see this, you probably need to get down to about 100 meters per second. So that's what we want to do, is actually get to 100 meters per second radial velocity precision so that we can detect these little tiny perturbers. So
Just to ask about I mean, if you want to not find the halos, how hard is that? Like, how hard is it to say, we've got 100, 200 streams,
and there's nothing.
and we didn't find any
Right.
that were small?
Yeah.
What,
Yeah.
like, how hard is it to like rule out that they're 10 to the 6?
I think you still really want the velocity precision.
No, I know you need
Yeah,
the
yeah.
velocity, for sure you need the velocity
Yeah.
precision,
Yes.
but I'm asking like, what else?
Yes.
Like, you need to be able to not find them
You need to be able to not
and
find
then show that that's interesting.
Yes.
And how hard is that second step?
Yes, I can't give you a full answer to that. All I can tell you is that we're working really hard on answering that question.
Okay.
Yeah.
The Anna video you showed was in configuration space. Here you're showing in velocity space. Why?
Yes. Why? Okay, so.
I just find it in configuration space.
Yeah,
That's
yeah.
where we found the first.
So for sure, there is information in density and in velocity. The information is in both. I actually think it's likely going to be easier to find the smallest things in velocity space. And that's what the preliminary stuff that, you know, I think it's a different signature, but preliminary things show, well, I'm going to show you in a second, but well, a little bit, but I think there's a chance we can get down to 10 to the 5 in velocity space. I don't think we can do that in just the density. Yeah, but I would say that this is still, so I don't have answers to all of these questions yet. And I'm disturbed that I don't have answers to these questions, but we're going to try to get the data anyways. So we're building 2 new spectrographs so that we can do this over the entire sky. So one in the north, one in the south, one will be on MMT, one will be on Magellan. And we plan to do a large survey, 5-year, 500-night survey with these 2 new instruments. So it's called ViaSpec. It's got 600 fibers with R of 15,000 and a narrow wavelength range. So in order to be able to get this resolution, to be able to get to 100 meter per second velocity precision, it's much cheaper if you just look at a narrow wavelength range. And in this wavelength range, you have 2 nice features. You have a magnesium triplet, which gives you precise radial velocities. And you also have a sodium doublet, which is really useful for detecting interstellar gas. And so we have a high efficiency spectrograph over this narrow wavelength range that has high precision. Okay, so this survey is actually going to have 4 key parts to it. It will do streams, it will do dwarf galaxies, it will do interstellar gas, and it will do transients with this other part of the spectrograph that we're putting on here called Boombox. It's just 36 fibers, you know, not super high resolution, but it's convenient because we will be on the telescope for 500 nights. If anything interesting happens, LSST is going to have a million things happen every single night. Some of those will be interesting, and we can get on, you know, we can get to them in 2 minutes if we want. There's a lot that can be done with that. And Ashley Villar is actually leading that part of the transient part of the survey. Because in these times, many things are challenging, but we have a fully privately funded spectrograph, so we are going fast. And we hope to be on Sky basically by the time we have the LSST Year 1 catalog, maybe even before that. So that's the plan. So we actually just spent a few days trying to hash out a lot of the science a lot of it needs a lot of work to really understand, but here's an example of why we want to go to that higher velocity precision. If you look at 1 kilometer per second and you look at what kinds of impacts you will see, there's just a handful and they're relatively high mass. If you can go down to 100 meters per second, you start to get a lot of these lower mass impacts and a lot larger numbers.
And this is at what magnitude is?
Yeah, this is at G of 21. Yeah. So we plan, so G of 21 is what we can do in an hour. And then we'll do some of the survey, some of the dwarfs will go to G of 24 with a whole night.
And by kick, you mean sort of like in your picture. a
Yeah,
transverse
so
to the-
imagine the thing just, you know, having an impact on the stream. Exactly. So this is, again, very preliminary, but this is an estimate of sort of how many kind of big impacts we will see per stream. But then we do expect a large number of small impacts that you can't like sort of see in configuration space, but you can see in the velocity distribution. And so just as a little example, here's GD1. The gray is an unperturbed version of GD1. The blue has halos just down to 5 times 10 to the 7, and the red has halos all the way down to 10 to the 6. And you can see, you know, even by eye, they do.
This is the answer to my question.
This is the answer to your question.
Yeah. Okay.
Yeah.
So you should see something.
You should.
Yeah.
Yeah.
Okay.
Yeah.
I mean, there's a little bit of an issue because
Yeah.
the generative models of these streams don't quite work yet.
I know. There's a big issue. Yeah. 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 No, totally agree. So there's interesting things to
There's
do.
good theory there.
Yes, exactly. So we will not just do streams, we will also do dwarf galaxies. There's 50 known ultrafaints now. We expect to find 100 more. The smallest of these have velocity dispersions that are a few kilometers per second. So many of them only have upper limits on their velocity dispersion. So VIA should be able to actually measure the velocity dispersion of many of those. We plan to essentially do all of the ultrafaints above -3.5, and then as many of the fainter ones as we can fit in the survey. Some of those will be done with these 10-hour exposures that I mentioned. And so we'll get the velocity function. We should be able to do the modeling properly that Mike asked about at the beginning. And so we're working on that hard right now. One thing that's great is we will have kind of big improvements, I think, to indirect detection limits, because those really do depend on the velocity measurements, especially of the nearest systems, and ideally actually map the profiles. Also, for every dwarf, we will go out to probably roughly 10 effective radii. So actually getting the stars in the outskirts will be really exciting to actually understand the tidal disruption of the dwarfs.
Sorry, I might have missed this. You're identifying binaries just with multiple. Okay,
Exposures, yeah.
All right.
Yeah, exactly. I mean, it's a huge problem. We're thinking about it a lot.
Yeah.
You know, yeah. Okay, so I'm gonna just spend the last, I don't know how much time I have left, but I'm gonna spend the last part on the theory side of this. So really excited about what these new surveys are gonna bring to all 3 of these probes. But in order to get that science out, we really need much better modeling. And so examples of some of the things that we need to be able to do better. Milky Way is only one system, and there's things that we can only measure in the Milky Way. We really need to understand its cosmological context. This is something I've been working on for a while, but I think we've made very good progress on that. Substructure finding in simulations is a mess. Most of it is done very poorly. We've recently made some significant improvements here. We need to think about how baryons impact the predictions. This is quite important, but most of it seems to be characterized by just the disk itself and how big it is and how it grew over time. And we need to be able to really make nice predictions for the stellar halos and the streams. So, you know, from my perspective, so I've been trying to model like the whole universe for about 20 years. And the way that I have always thought about this is that we need to be able to get as close to the data as we possibly can, and we need to do it fast so that we can be flexible. And that I think has been very good for large scale structure. And I think we need to do it in this regime as well. So we need to really be able to produce statistical samples of realistic Milky Way-like systems in the full cosmological context. My hope is that, we can make sure that the theory is not the limiting factor. That is a tall pole, actually. I would say certainly right now it is. This nice plot from the review article I wrote with Jeremy, mostly we've thought about this in the context of large scale structure, kind of going from these very expensive hydro simulations over to, very empirical models. And I think in many cases, the sweet spot is in between, because we know a lot about how structure forms. This part is wonderful, needs to be done, but is very hard and very expensive and very uncertain. And so being able to marginalize over it is very important. These are kind of too simple. And for some purposes, that's fine. If you just want to measure a 2-point function, that might be fine. But if we really want to be able to predict a whole stellar halo, it's probably not good enough. So I think the sweet spot is in between, but I think moreover, this is actually a pretty big effort to do this right. We need to do it in a way that is fast and flexible, and kind of in a similar spirit to how we have approached large scale structure. So I'm going to talk about what we need to do and what we're working on now. So these are all pieces of the modeling pipeline that I think we need, that we are working on. Some of these we've done, and some we're just starting. So the first thing is to actually have a reasonable statistical sample of Milky Way-like halos. So we've done a preliminary job at this, so have about 50 Milky Way mass halos that are just selected on mass, and then another sample that actually looks more like the Milky Way with an LMC and Gaia Enceladus kind of coming in at roughly the right time and with the right mass. That's really important, especially the LMC piece. The LMC was created relatively recently in the last 1 to 2 gigayears, and it's pretty big. So it actually has a significant impact on the predictions for what is happening in the Milky Way. We found in that analysis from DES and Pan-STARRS that we actually could not match the data if we didn't have an LMC at the right place, because the actual satellites in our galaxy are anisotropic. There are more in the direction of the LMC. So that's a key piece. We need to understand the impact of the disk of the Milky Way on substructure. So basic idea is you've got a disk there. It tends to disrupt the satellites more than if you didn't have that. We have not solved galaxy formation, and so this is a hard problem. Actually simulating with full hydro a Milky Way down to redshift 0 with all of the physics you want is extremely expensive. But it does seem that most of that can be characterized just by an evolving disk potential. We really need robust substructures tracking. I have one plot I'll show you about that. We need to do higher resolution halo realizations, and we're actively working on benchmarking the codes and getting started on that program. And then I don't think we can in the next 5 years do full hydro for the whole program, but we should test our assumptions at every point with as much physics as we possibly can. Then we need to go from the dark matter simulations to the observed property of stars. And so we've been working on ways to do that are kind of sort of inspired by things we've done in galaxy formation, but really sort of an empirical forward model to populate dark matter particles with stars and then see what happens to them. So I'm just going to show a couple of plots on that. I know I don't have a lot more time. I'm not going to go through this, but if anyone is really interested in what our pipeline is, this is what we're thinking about. So just a quick thing on this predictions of the subhalo populations. When I said, we really need to, if we want to say, okay, here's how many things pop through a stream or are sitting in the strong lens, we better know how many CDM predicts. I don't think we know the answer to that right now. And here are 3 examples of things that impact the prediction of substructure. So one is the presence of the LMC. So recent LMC accretion in the inner halo can lead to 80% more substructure than you get without an LMC. The second thing is the disk. So here we did sort of self-consistent disk growth, populating the Milky Way with a universe machine growing galaxy that has a nice star formation history, and the disk grows in that way. So the disk can reduce the subhalo significantly, but it depends on the disk halo ratio, and it depends on the accretion history. Actually, a lot of the disruption happens roughly at redshift 1. And so the Milky Way likely actually has more disruption than average because it is a more massive, it has more stellar mass per halo than a typical object. So that's an important thing to take into account. And then the next thing is that halo tracking matters, and almost everything you've seen in the literature does it pretty poorly, especially in the inner regions of halos. So I will pick on my own work to critique this. This Rockstar Halo Finder, which we developed in my group and has been very popular. If you can see that tiny yellow line there, Rockstar loses a typical halo after a few orbits. That's very common for modern halo finders. It's not done better in hydro. So don't fool yourself thinking that hydro has solved this. So we have a new thing that actually tracks the particles over time and can, really keep things for 10 orbits instead of 2. There are a few other recent halo finders that are using that kind of information, but it can be, a factor of 2 in the inner regions. So it's quite important to do this right. What we haven't done yet is put all of these pieces together. So that is coming, but I think this gives you a sense of where the uncertainties are. I am probably out of time. So I'll just say really briefly, we've got a new approach to kind of populating dark matter particles with star particles that have properties, and then pushing those forward. And I just want to show one nice movie. So this is something that comes out of that star tracking procedure. Here on the left, we have dark matter halo, Milky Way mass. And we have basically labeled its dark matter particles with stars. And the thing you're seeing here is that actually what we did in this example, it's just a visual example, is to show that if you change the size of the galaxy, you obviously change how it disrupts. So in this case, we made a really big puffy galaxy, and in this case, we made a really compact galaxy. And you can see, what you actually see for the stellar halo is very different. So this is something that we want to, both play with and then marginalize over.
What are the axes on the bottom?
Oh, I'm sorry. This is radius from the center of the halo. So, and then this is velocity. So this is 0 velocity here. So these are just particles coming in along the Hubble flow and, coming around.
All of the stars in these stellar halos come from subhalos that have been stripped.
Yes.
Or not. Okay.
Yes.
When people, sorry, I know you're out of time, so I apologize.
No, it's fine.
But apologizing to everybody else. But in this game, there's this talk of like in situ versus not stars in the halo. Is that, are you assuming that there are no in situ, or what is that?
I have decided for the near term to ignore the Milky Way itself.
Okay.
And that is because I'm mostly going to focus on things well outside the Milky Way.
Okay, so you're going to be in a region of radius where the
that is
in situ
not
fraction
important.
is very low.
That's right.
Okay.
Yes. So that can be added in the future, but right now I'm going to focus on that region where the in situ fraction doesn't matter.
Okay.
Yeah. Okay, so I'm out of time, but I'm done. So just to say that I think there are new ways to probe small scale structure. We have very exciting new data. We will need new models to interpret these data. And I'll just verbally say a couple of highlights from my final slide, which is just that I think there's a wide range of dark matter models that these kinds of constraints can probe, and that's really exciting. So including ones that I know nothing about. So if you have a model that is interesting, that's great. Really exciting data coming at us, and I am personally very excited about this kind of achievable thing that I think is possible in the next decade to really find these halos below the limit of galaxy formation or convince ourselves that we are not finding them. Thank you. I know there's questions.
Yeah, well, I always have questions. One is, I believe this is true, but just confirm, no one has ever found a massive object that doesn't have stars in it, right? It appears that every dark matter halo, every massive dark
I
matter
think
halo
that's
has
right.
stars.
I think
And
that's
we
right.
don't see galaxies that don't have their requisite amount of dark matter.
I think,
And
you
is
know,
that surprising? Like, do
There-
simulations fully, well, you don't work on that side of the simulations, but do the simulations?
yeah, so, I mean, I think above a certain mass, you really should expect that every single halo has a galaxy. Just don't understand why you wouldn't get a
You
galaxy.
mean the failure rate is below 1 in a billion? I mean, that's a pretty strong
10 to the
failure
12?
rate. Well,
Yeah, I mean, depends on what mass we're at 10 to the 15, yes. 10 to the 12, I think probably yes, but I certainly can't guarantee that.
I mean, it'd be interesting to know whether the simulations confirm that.
I'm not aware of any simulations that have reasonable resolution that predict a 10 to the 12 solar mass halo without a galaxy. Now, there is debate about the other side, right?
A galaxy
Like,
without its also.
there's debate about the question of, are there galaxies without dark matter? And, you know, there are formation mechanisms that you can imagine, you know, interacting galaxies or interacting tidal tails where you actually get something that looks very much like a galaxy and has no dark matter. Actually, as a side project, so I've been talking on Friday, I spent time talking with Peter Van Dokkum about that second part, which is that with the spare fibers on VIA, we could just get velocity dispersions for a large number of dwarf galaxies nearby, and maybe some of them will have no dark matter. That would be interesting. Yeah, I think it's not well known what those statistics are, or you know. And I made this schematic sort of
You
follow
mean
up.
resolve dwarf galaxies?
I mean, no, I mean just like 10 to the 8 solar mass systems at 30 megaparsecs.
10 to the 8 in stars.
Stars.
Yeah.
And
We know a fair amount about those. There's,
right, but do we know any that don't have dark matter? Have we explored?
yeah, there's a lot of H1 data on
There
those,
is.
right?
Yeah.
Alfalfa
No, for
has
sure.
many
Still up.
galaxies like that.
Yeah,
Yeah, they,
There's no evidence that they don't have halos.
right.
Exactly.
Yeah, there are, I mean, there are some H1 detections without stars.
Yes.
I think there's like a tiny number of those now.
Right.
Sorry, can I question the first half of David's premise? How would I measure a dark matter halo without stars?
Gravitational lensing
How do you
seems
know to look
sensible.
for the lens?
Well, it
Like,
could
what do
have
you think
gas.
what do you think the selection function
You
is on
find it in
strong
gas.
gravitational lenses? We go and we
Oh yeah, you can find it in gas.
we can what? Oh, you
But
sure.
it's gas.
If you have gas, sure.
Yeah.
Okay.
If you have gas, yes. So we should look in the H1 surveys for the things that have no stars.
But I mean, you could in principle find the lenses, right? Strong lenses.
Yeah.
In principle, for sure. In
Hard to
practice, like the
imagine
way we
gas
actually.
would be held together well enough without dark matter, not to also then form stars. That seems,
Yeah.
that would be paradoxical, I would.
That's the hard part.
If there's enough massing.
There's
gas
there
to-
I think are a handful, by which I mean 1 or 2 controversial cases of H1 detections without any sign of stars.
There was one like a week or two ago that had rotation.
But that's okay, Mike, if it's got dark matter to hold it together. That's all I was saying. If there's enough gas that by itself gravitationally.
Sure, but he was also asking, are there big dark matter clumps that maybe do have gas but don't have any stars?
Just things are looking really universal, like
I know.
disturbingly universal.
Disturbing. Yeah. Right. I'm not sure it's disturbing yet, but you would have, like, I guess I would say you would have to characterize it better to know whether it's disturbing or not.
Right, I mean, that's part of the point. What you focused a lot on, like, it feels to me like 2 of the big issues here are having this model, like this thing about doing the lensing. The lensing relies on having this kind of some kind of very strong, very accurate prior belief about what the background sources can look like.
I
somehow.
don't think you have to have a strong prior belief if you have a source catalog that has all sources that exist.
Yes, which is, that's what I mean by your strong prior belief,
Yes,
is that you have a representative set of source galaxies. And then on the streams, it feels like a lot of the issue is having correct generative models of these cold streams. And right now, I don't think there's any stream where we can model the morphology of the stream accurately.
Yep.
Which, you know, maybe it's because they're all getting beat up by 10⁷ solar mass dark matter halos, or it could be because we
Yep.
have something wrong. And the methods we use to simulate them are pretty gross right
I know.
now, because you need to do this releasing of stars.
No.
And it's all
I know.
made up, really.
I know. So I, you know, I
That
think,
seems harder than the cosmological part of this. You know, you're saying like we need to improve all these things about the cosmology. I agree with all of that completely, but it feels to me like the streams might be even harder.
I mean, yeah, I
And it's
agree.
critical because they are these beautiful cold antenna.
I know.
So like it is a very nice,
I know. I mean, we have to have a properly evolving potential that is not smooth.
yes, exactly.
That's
That
the-
itself consistently contains stars that can
Yes.
fall out of it.
Yes. Yes.
It's like it's.
But I
It's
don't
hard
think
work.
it's possible.
No, I like
Yeah.
to keep working on it.
Yeah. Yeah. Okay. Thank you.